So hello, everyone, and welcome. Thank you so much for joining today's first session in Third Derivative's Data Center Decarbonization Series. My name is Cheryl Webster, and I'm a Senior Associate at Third Derivative, focused on our startups decarbonizing the built environment. We have a very exciting session for you today, including abbreviated expert insights from our very own Lindsay Rasmussen, taken from our recent Data Center Decarbonization thesis. These insights will be followed by 4 startup pitches from highly relevant companies who are focusing on data center partnerships. Now, each startup will have about 7 minutes to pitch, followed by 3 minutes of Q&A. And for the next hour, we simply ask that you be present and encourage you to ask thought-provoking questions of our presenters. You can send in those questions via the Q&A button at the bottom of your Zoom screen. And yeah, without further ado, I will kick things over to Lindsay, our research expert and our moderator for today's session. Lindsay?
Great, thank you, Cheryl. And yes, welcome everybody. We're excited to be hosting this data center startup showcase. As Cheryl mentioned, I lead Third Derivative's building sector efforts. I'm on our research and diligence team. I'm going to set the stage with some insights from a recent investment thesis we completed on data center decarbonization. And then we're really excited to hear from 4 of our startups in their pitches today. So to get us started, what are data centers and why are they necessary? Just to level set. Data centers are a big topic of conversation right now, especially in light of growth in data centers, in light of that growth in energy consumption as well. But why are they so important? Data centers really are the backbone of the digital economy. They're the physical structures that house computer servers that are used to store, process, and deliver data across the world. We typically picture huge facilities when we think of data centers, but in reality, they range in size from a closet in an office building all the way to now as big as 13 football fields in size. So a huge range and variety there as well. And again, really critical because data centers handle over 95% of the world's internet traffic. So they're crucial both to digital economy, but also to issues like national security. There are 3 primary types of data centers today, and that's enterprise, colocation, and hyperscale. Enterprises are run by businesses for their own use. This makes up about 28% of data centers today. Colocation data centers lease space to customers to house their own computing and storage equipment. These make up about 36% of data centers today. And then hyperscale data centers are often the largest. They house thousands of servers and equipment that can support the cloud platforms that are used by millions of people at a time. Hyperscale data centers are often owned and operated by major tech companies like AWS, Meta, Google, et cetera, and make up about 37% of data centers today. I'll note this is up from 10% as of 2010, so it's a sector that's experiencing a lot of growth. So what consumes electricity in data centers? That's typically largely the IT equipment, so servers, storage systems, and networking equipment, as well as cooling systems, and then other infrastructure like lighting and office equipment. Servers make up the biggest portion of this energy consumption. As you can see, it's about 61% on average for all data centers. As you can see, though, this varies quite a bit by those different data center types. So enterprise data centers are often smaller, they can be less efficient. That means that cooling makes up a larger percentage of total energy consumption. Hyperscalers, on the other hand, are the larger ones. They're the most efficient. And here, cooling is about 7% of total energy consumption. All of that energy consumption adds up. So today, data centers consume about 2% of global electricity. This growth has been driven largely by increases in colocation and hyperscale data centers, as you can see in the left graph here. And then electricity consumption growth has largely been driven by servers, which again make up 61% of data center energy consumption on average, and has increased substantially over the past decade plus. Cooling is growing, but has also remained more constant thanks to consistent efficiency improvements over time. As we look forward, we know this growth trend is continuing and is largely fueled by AI. So it's expected that global data center demand will triple by 2030, and that's with a growth rate of about 22%. And AI is a key driver of this growth. It's being pushed by massive growths in available data that's used to train models, improvements in computing power and reductions in cost for that, as well as breakthrough algorithms and architectures that are used to train models as well. Um, and AI is a major driver for growth in data center capacity, but other drivers include growth in cloud migration, software as a service models, increasing the digitization of public services globally, as well as things like accelerated tech trends. And as a result of this continued surge in data center demand, we're expecting that energy consumption will reach about 9%, or sorry, of electricity by 2035 in some regions, especially in the US, which is the largest market for data centers globally at the moment. Globally, this will likely be about 4% of total electricity consumption by 2035. And data centers are growing to become a major contributor to overall load growth. That said, there's a lot of unknowns associated with data center growth, and therefore with their energy demand requirements. The IEA graph here on the right shows the degree of this uncertainty. And while growth is occurring rapidly, data centers are also facing serious headwinds at the moment, which may slow this growth to an unknown degree. First, data centers require huge amounts of power, especially those large hyperscale data centers, and existing grids might not have that capacity available. So that means that capacity growth is needed on the grid. That can cause delays in grid interconnections and permitting processes, supply chains for key energy equipment, as well as key equipment for data centers as well. So beyond those unknowns, there's also unknowns in the rate of adoption for AI, if model advancements will significantly drop energy demand over time. And generally, there's a lack of robust publicly available data on data center energy and material consumption. So unknowns in terms of this growth overall. As Cheryl introduced, Third Derivative recently completed an investment thesis on data center decarbonization. We dove into computing, so the main function of data centers, cooling, what's absolutely necessary to keep that computing functioning properly, building construction, so the physical facilities themselves and all the materials that go into that, and power, so how we're actually powering these facilities. And I'm just doing a really short snippet of it here today for you all, but our full investment thesis dives into the state of the market, much more technical detail on leading and emerging startups in the space, startup landscape mapping, and provide some investment recommendations. So if this is of interest, please reach out to myself or anyone from Third Derivative here if you'd like to talk more about the research we completed as a part of this effort. For today's startup showcase, we're highlighting innovations within these first two categories, so computing and cooling. These are critical categories and have a lot of opportunity for emissions reductions. Cooling and computing are both high electricity and emissions intensive aspects. They're also critical for data centers and aren't going anywhere. But the reality is that by adopting advanced energy efficient IT, which includes visualization, storage utilization, and advancing efficiency improvements for cooling, we can actually reduce energy consumption in data centers by up to 70%. So a lot of opportunity with both of these categories. To touch really quickly on computing. So computing encompasses several subcategories. This includes power electronics, hardware, software, chip design, quantum computing, much more. There's a lot that goes into data centers. But today we're going to focus on the power electronics space, which is really critical to support the expected 3 to 10-fold growth in rack power densities this decade. To give a little bit more context here, so before the explosion of AI, a data center single rack used to consume less than 60 kilowatts of power. Today, 100 to 200 kilowatts is more than norm. And with AI models evolving rapidly, it's expected that the next generation of racks will reach 600 kilowatts to even a megawatt by the end of the decade. And so that will require new approaches to power distribution and power electronics, and namely a shift from AC power to high voltage DC power at the server. And this is necessary, but also advantageous for a couple of reasons. So DC power can enable higher efficiencies because there's less conversion losses. Because there's less conversion losses, there's less waste heat entering the space, so that reduces your cooling demand. It can support renewables integration because batteries, PV, et cetera, are inherently DC voltage. And it can also save on cost, complexity, and space. For example, AC requires hundreds of pounds of copper per rack at moment. So there's opportunities to reduce the dependency on a really critical material there. So data centers will need to upgrade their hardware to support this. That creates a big role for innovation and a need for really efficient and smaller power devices. Enter the two startups we have pitching today from the power electronics space. Both are focusing in on solid state electronics, and we're excited to hear more about their innovations in a minute. We have Blixt, who provides solid state circuit breakers, and DG Matrix, whose solid state electronics are really important for conversions within data centers. So increasing power density is requiring new approaches to power distribution. It's also requiring different approaches to cooling. So as power densities increase, so does the amount of heat generated and the amount of cooling needed. And this is forcing a major shift in how we cool newer data centers, and is making us revisit how we're cooling our existing data centers as well. So today, data centers use a mix of cooling approaches. To date, air cooling approaches make up about 80% of data center cooling. However, liquid cooling is becoming necessary, especially for AI specialized servers that have really high power densities and generate a lot of heat. As a new hyperscale data center today, for example, is likely to deploy liquid cooling to the chips and the servers directly and have air cooling supplement that to address ambient temperatures and adjacent office spaces, for example. As with computing, there's also a lot of room for innovation in the cooling space. We'll need next generation cooling solutions that can handle the heat rejection and cooling demand of really high power density racks. So moving past even this 200 kilowatt, what's viewed here on the screen. We're also going to need innovations that can expand the cost and efficiency ranges and bands here for existing cooling solutions. And that's largely air cooling. And so we have exciting companies joining us today that are focused on the latter. Heat Inverse is providing energy-free cooling via passive daytime radiative cooling solutions. And Blue Frontier is advancing the efficiency of air cooling systems using liquid desiccants. So with that, I'm going to roll out the red carpet and invite our first company to present on the computing side. I believe we have Blixt up first. So with this, I would invite Blixt to present their screen, and we can pass it over to them for their presentation.
Wonderful. Thank you so much. You see my slides now, right?
Yes. I think it's switching over. Okay.
Yeah, you see the slides, right? So we are Blixt, we are based in Sweden, and we are the creators of programmable power. So in essence, turning electricity to a digital platform. And as you already mentioned, I mean, supply side have been much, much cleaner. We are rolling it out in a really nice speed. But on the other side, the demand is exploding. We know that data centers are the most volatile and energy dense loads that we ever built. Where we are stuck is in the middle. That hasn't changed much. We're still very old analog mechanical equipment that is not designed to shuffle around the right power to the right load at the right time. And the core of the problem is switchgear, and that is a generic term for devices that protects electrical systems, they meter and they turn power on and off. But here's the thing, they are all mechanical, analog, one single purpose, not designed for this century. So what we do is that we collapse all of that fragmented legacy hardware into one unified device, which means that we could software program this device to handle AC and DC at the same time, which is already said that is super important for DC data center growth. So power is now going through the same shift that we have seen happening before when phones became smartphones, network boxes, SDN networks, and mechanical switchgear is finally becoming software defined. And when that happens, it also unlocks completely new values. We've seen it with Nokia collapsing, Apple building $1 trillion company. Switchgear market is worth 160 billion, and that will be the next big transformation. And once electricity becomes programmable, you get real-time visibility, software control of the power flow in real time, and milliseconds fault response time and continuous data. So what we do, in essence, we're building up the hardware platform or the hardware devices infrastructure in combination with an intelligent control layer to connect electricity with software and AI. And the applications that are relevant, I mean, for all segments, but in the data center space in particular, is real-time rack level power visibility. We have sub-millisecond fault isolation, which means we can avoid downtime and interrupt before those faults happen. We can work with peak shaving during the AI surges and make sure that we can allocate the right power to those servers that need it the most. And also enable the DC architectures, because AC and mechanical switchgear is not designed for fast DC currents. So I will walk you through relevant use cases that are in industrial manufacturing and grid operations that we've been running now throughout the last year. And this could equally be a data center, but in this case, we're working with Sanmina Industrial Manufacturing. They're the largest fourth largest EMS producer in the world with 80 factories. They are still modern, but they have no insights, no control over the electrical distribution, which means that they have tremendous energy costs. And this factory in particular, still in Sweden, it's modern, but they have 5 to 6 blackouts per year. So we go there with our solid state switchgear. It's easy retrofit in the existing cabinet, no special infrastructure required. It's quite mind-blowing what we unlock with the real-time visibility and control. They estimate that on a full-scale deployment, they have payback in 12 months. And that is because we can identify idle equipment, make sure that we optimize energy and reducing the downtime. So we're now entering into commercial agreement with a second order, and the joint plan is to roll out to all the factories. Vattenfall is also relevant. I mean, like any one of the grid side, we are facing massive upgrade costs for just over-dimensioning the grid with newer equipment. So what we support Vattenfall with is intelligent load shedding and shifting. We install behind the meter, connect all the loads, which is way much cheaper than just building the old backbone and providing full control. Again, load shedding and shifting is equally important in industries and in data centers. So again, we are rolling out. It's so nice to see that 100% of our sales funnel is now converting into contracts and repeated orders. So we start where customers already pay for this problem. They seek better alternatives, and we can support them with that. So we are also have agreements in the defense sector with Swedish MOD, this, again, for resilient infrastructure. And in the data space, we are currently speaking to several players, but we are happy to onboard more pilot customers. And our business model is both selling hardware per use, but also charging on the software platform license and per application. One more thing, this year we're adding to the platform the Xverter, which is for voltage conversion. So it's a software-defined battery that you can program to absorb and deliver any kind of AC or DC output, which we will install both as backup power and to supporting those customers that we already have. So think of it as a UPS or a BESS system in the data center space. So we're a team of 20 people, hundreds of years of experience in electronic software, scaling large digitization projects. We are backed by ERV USV, also third derivative, so thank you for that, and co-funded by the European Union. So 2 takeaways for the audience. We're raising 20 million to own the control layer of power distribution, using that money for scaling deployments, operation, expanding all the applications on the platform, and establish leadership in this category. But also, again, if there's anyone in the audience that are keen to try out new technologies, we are looking for more pilot partners in industry data centers and grid. So thank you so much, and happy to take the Q&A.
Amazing. Thank you so much. We do have a couple of questions that have come in, so we can jump right into it. The first one was...
I will co-host this with my CTO, Jens Peter Schröer. So if you see a male with beard answering, it's my co-founder and CTO.
It very is perfect. Okay, first question for you all. So how do you view the grid's limitations as a bottleneck for AI and electrification?
Uh,
Go ahead, Charlotte.
Yeah, I think it's easy because if it's analog and mechanical, I mean, we have from the supply side, we have renewables that we cannot board to the network. And on the other side, data centers are not getting permit, so we need to unlock more flexibility, and you cannot do that fully unless you have real-time data and insights to intelligently work with all the loads in the network. But you had some more points, Jens.
No, exactly. I mean, a lot of this about the capacity on the grid and then be able much better control, and also about the situations where it's the extremes, if faults occur on the grid, because that's normally when the differences are. So a lot of the capacity planning takes the faults into account. And with the speed that solid-state switchgear brings to the table, you can do a completely different fault planning, meaning you unlock capacity which has been blocked up till then.
Great, thank you so much. The next question we got in for you is, where do you see the biggest need for intelligence at the power layer? Examples being load balancing, failure prediction, or process optimization.
The intelligence is needed in different flavors on all the different stages. So different parts have different requirements. So I wouldn't say one of them has a higher need than the other ones. There is, downtime in terms of machine downtime is a very costly thing. Downtime in terms of you have power outages or power fluctuations and machine fails due to that is also a very costly thing. So different parts have different needs, but it's in general there where the high growing power demand is. So the facilities has one, industrial facilities, and also the data centers have a very high sensitivity to these ones currently.
Great, thank you. And for the audience, just a reminder, you can add questions into the Q&A. Unfortunately, I think we're at time for questions with Blixt, but I want to say thank you again so much for the presentation and for joining us. We have a poll that just went up if you're interested in being connected with Blixt or have more questions for them specifically. And as always, feel free to reach out to the Third Derivative team, and we're happy to make connections as well. Perfect. So with that, I'm going to go ahead and invite our next computing and power electronics startup up, which is DG Matrix. So when you're here, feel free to share your screen and we'll jump right into your pitch.
Hello, good day. Can you hear me clearly?
Yes, go for it.
I'm Harun Inam, CEO and co-founder of DG Matrix. We're bringing a multi-port solid-state transformer to the market. And we are a behind-the-meter solution that aggregates multiple energy sources for augmenting the grid power. Today, we have about 9 gigawatts of production capacity coming online in the next year to year and a half for our data center solutions. Our deployments have been live since 2024. April of 2024 is when we installed the first multi-port solid-state transformer. And today, we are 260 plus engineers with 15 PhDs representing every major discipline to do a fully vertically integrated solution. We are lucky to have a lot of large corporations, those with the gangs of PhDs, engineering PhDs, always seem to gravitate towards DG Matrix. The challenge for AI data centers is getting enough power. Other than China, every other country has an issue getting more and more power from utilities. It's the upgrade timelines, it's the interconnection studies, its lead times, and its integration of behind-the-meter power. In addition, AI pulse loads, which are generated in the learning mode, are very heavy. They're 2x the power requirement multiple times a second. And it's such a nasty power requirement that it has ripped off shafts from all generators and degraded all lithium-ion batteries prematurely. So solutions are needed at the multi-megawatt level in a modular fashion to handle this. DG Matrix multi-port solid-state transformers It's the only architecture that can seamlessly blend multiple AC and DC sources, such as fuel cells, natural gas gensets, diesel gensets, batteries, or any other AC or DC source with the grid, and blend it in thousandths of a second or faster to mitigate pulses and provide much more power behind the meter cheaper. Our solution is 1/2 to 2/3 the TCO of any other competitor by adding up the CapEx and just by the CapEx alone. Leave alone that we have higher efficiency with far less components in the delivery chain. We eliminate stranded power at site, and just as a metric, every dollar, every watt of power generates $10 to $12 of revenue for AI data centers per year. So if you can get 10% more power, unstranded through power routing, dynamic power routing, let's say for a 100 megawatt data center, that's 10 megawatts, that's 100 million to 120 million of annual revenue that you're unlocking. So the value provided by our architecture is immense. Because it's such a consolidated solution, as we'll show you, we can have or much better take the installation time down, because the number of components crunches down from 11, 17 components down to 1. In addition, we are a future-proofed architecture, as we can handle AC and DC out of our universal ports at the hundreds of megawatts level, ganged up in a modular fashion. And we also mitigate the AI pulse loads. To show you how legacy architectures, there's many legacy architectures. So I'm showing you one representative one, but we have a library of these, and we can compare any relevant one. But here is the distribution network coming in from the very top through a step-down transformer and protection. The battery is hooked up with a DC to AC converter or inverter, isolation transformer and protection, and then it heads off into the data center with a classic UPS and an IT load, and then the AC generator can be brought in for switchgear. DG Matrix replaces all components in gray. This is our solution. We are the only solution to deploy multiple ports that can add the raw battery, the raw AC genset, and the distribution network's voltage seamlessly into the power router and deliver it to a sidecar or deliver it directly for 800-volt DC architecture, either one. We have compared ourselves to almost every other manufacturer out there, and our metrics in CapEx and footprint and installation time are leading. With that, that's the end of my presentation, and our ask is if you could introduce DG Matrix to developers of data centers as well as operators and NeoCloud platforms. We'd be thrilled. We do have a significant pipeline, but with this expanding team, soon to go over 300 engineers, we're happy to deal with more demand. Thank you very much.
Great. Thank you so much. We do have a handful of questions for you. I'm so excited to jump into that. It seems that DG Metrics has been in the electrification market for a little while, and it'd be nice to get some more information on how you scale your solutions from the electrification market specifically to the data center market.
Yeah, originally we started with fleet electrification, EV electrification of fleet, because 3 years ago it was a very hot market. And we focused on 800 volts DC because that's what was needed for trucks and charging cars faster. So we happened to have it, and one day we got a call from the biggest chip maker for GPUs, and they said, "You really have this," and that's what got us into thinking, how do we parallel these machines? So today, our building blocks are 400 kilowatts going to a megawatt class building block, and then you parallel these to get up to tens of megawatts, and then you parallel those to get up to higher power.
Great, thank you. And what would you say differentiates DG Matrix from other solid-state transformer companies?
We have multiple patents on multi-port solid-state transformers. We're the only ones that can aggregate those multiple sources and deliver simultaneous multiple loads. Nobody else has that. That is the architecture you need for eliminating stranded power, for having the highest efficiency and the lowest CapEx and the lowest installation footprint.
Great. Perfect. And then for data centers specifically, as you focus in on that market, what would you say is the core value proposition for the DJ matrix transformers for data center developers and operators?
The speed to power. I think we were at a very special event with some noteworthy people in December. And the number one thing that this leading hyperscaler company mentioned is no one can get enough power. Behind the meter power is the best way to go for now, unless you're in China. And so for the majority of the world, we have the best solution for aggregating behind the meter power.
Great. Perfect. I'll go ahead and pause and see if anyone else has questions. Feel free to put it in the Q&A or the chat. And then if not, we can move over to our cooling startups. We'll give it a minute. Okay, great. We got one more question. Do you have a new design for the transformers?
Yeah, we have a very innovative team. So we're always trying to get our power density up. We're working on increasing our reliability. We're compliant with the 5 nines with our paralleling architecture. But yes, we are working on a series of things, some that we can disclose today and some that we can disclose under NDAs. But we have both low voltage solid state transformer solutions that we can apply starting Q2, certified solutions. And next year we'll be going to medium voltage 35 kilovolts input straight to 800 volt DC architectures.
Perfect. That's super exciting. Okay, with that, I guess thank you so much to the DG Matrix team. We did just launch a poll, so if anyone in the audience here would like to be connected to DG Matrix or has more questions you would like to discuss, feel free to answer that via the poll, and we'll make sure we get it to Haroon and Michael and team. So we'll give that just a couple seconds, and while we do that, we'll go ahead and ask you two I guess you've already stopped sharing, so we'll just transition to cooling. We have heat inverse up first with Dr. Romy Fain. So we'll have you share your screen and then we'll jump into that. And Cheryl, yes. Perfect. Okay, go ahead, Romy.
All right. Good morning, everyone on the West Coast. Afternoon for those of us on the East. My name is Romy Fain. I'm the founder and CEO of Heat Inverse, where we make thin films that get cold without any additional energy input. My background spans 3 main areas that directly show up in this product. I have a PhD in electrical engineering from Cornell, focused on mid-infrared photonics research, a bachelor's in mechanical engineering from UC Berkeley, focused on thermodynamics research, and 2 decades as an entrepreneur in manufacturing and prototyping, beginning in the San Francisco Bay Area. And all of that experience goes into what we're building at Heat Inverse. We're making scalable, durable, real-world applicable metamaterials to dissipate heat more effectively. Our mission is to revolutionize cooling technologies and profitably reduce greenhouse gas emissions by at least a gigaton at full deployment. Rising temperatures are exacerbating problems across many industries. With data centers, heat directly impacts reliability, derating, operating costs. Similarly, the electric grid is seeing reduced efficiency, more frequent derating, shutdowns under thermal stress. And heat is also a real issue across many other sectors, including buildings and solar and transportation and EV infrastructure. At Heat Inverse, our passive cooling thin films increase reliability, efficiency, and asset lifetimes, decrease maintenance costs and greenhouse gas emissions. And this is a ready-to-deploy, high-impact solution that is very simple integration. And we do all this with no moving parts, no power consumed, and none of the waste heat that's generated like from conventional cooling systems. How it works, we make these materials that selectively emit in the wavelength ranges where the atmosphere is transparent. And in fact, it's like removing the insulation between a hot surface and allowing it to escape past the atmosphere so that it cools without any additional energy input. And now we've seen 10 to 30 degrees C of temperature reduction at customer sites, with higher temperatures leading to more cooling capacity, which gives the system a degree of self-regulation. Here's a few examples from the dozens of paid pilots we've deployed so far. At one battery energy storage site, we've demonstrated over 25% reduction in auxiliary power, where the customer was only targeting 10%. At another site, the films kept inverter temperatures lower than the shade structure, which is our closest competitor in that area. At a peaker plant in Los Angeles, we saw up to 25 degrees C difference on identical transformer cabinets. And on refrigerated containers, we demonstrated a 28% reduction in compressor cycling. We've seen similar benefits across a range of assets and electrical enclosures supporting batteries, inverters, and other heat-limited infrastructure. In a preliminary data center test on outdoor piping we use for coolant flow, we demonstrated a peak temperature reduction of about 38 degrees Fahrenheit. This customer was only looking for about 1 degree improvement to justify moving directly to deployment. Here's some examples of partners we've worked with across utilities, grid infrastructure, data center development, and related deployments. Now, at this stage, we're looking to deploy for deployment-oriented more engagement, specifically introductions to data center operators, utilities, EPCs interested in pilots or direct deployment where uptime and reliability really matter. And here are a few examples of the types of deployments we can do on data centers, both hyperscaler and modular systems, inverters, transformers, and other types of power generation equipment that is associated frequently with these data center deployments. So thank you, and I'm looking forward to hearing some of your questions.
Amazing. Thank you so much, Romy. I might actually start with a question from myself. So I know your product can be applied to so many different applications. With data centers specifically, is this being applied to like the roof as a layer, to cooling pipes? Yeah, how is the product being applied for data centers specifically?
That's a great question, because initially I was thinking that it may only have an application on the modular ones because it's a very similar form factor to the electrical enclosures that we've done in the past. But our initial motivated customers have been with the hyperscalers to put the films on, for example, the cooling pipes, the pipes that carry the coolant, and also on the AC units, those RTUs that frequently you see on the roofs or next to the buildings. We've shown and worked with other customers who manufacture that type of equipment, and we have a really large impact on those kinds of systems as well.
Great.
Oh, and also we can reduce, sorry, well, we can also, there's so many different applications, right, as you were saying. So the other thing is you can just reduce the load to cool the whole building. So you can put it on the whole roof and lower the ambient temperatures indoors.
Amazing. And yeah, there's a great follow-up question to that from Josh here. So can you speak a bit to how much you can cool the internal temperature of a building? And I might expand that too, since the other application is like application to coolant lines, how much you can reduce the temperature of that as well.
Yeah. So there's two different types of systems, right? There's one that has, an active cooling system, and that active cooling system will keep the temperature at the same set point temperature, or attempt to. A lot of times the cooling capacity of these systems is maxing out. But we also have applications where there is no cooling system. So on those applications where there's no cooling system, you will change the temperature of the inside of the box effectively, right? So on systems where there's an active cooling system, we've seen 25% reduction in load or more, depending on the circumstances and the system overall and where it is and all of that. But for temperature differentials, we've seen, up to 30 degrees C difference between with and without at hotter sites and hotter equipment. The hotter it is, the more it cools. So you'll see a bigger difference between with and without when it's on a situation it's really soft, very hot. So hopefully that answers your question.
Yeah, I think so. And if not, feel free to put follow-ups in the Q&A. I know we're focused in on data centers, but one question that came in from an M. Solomon is, can these films be applied to other applications like Windows for residential cooling, or do you see opportunity for scope in residential applications?
Absolutely. Yeah, it's the applications. So we're based in Ithaca, New York. So we have cold winters. So it's just a larger application area here, but also in a place that has winters is not the first place where we're starting. Definitely think it has a big impact on buildings. And we'd like to work with customers who have buildings, ideally 2 buildings that get the same usage and have the same, architecture. So we can do a back-to-back test, and that makes it very compelling argument, very compelling data.
Great, thanks. We've gotten a couple questions about performance in different conditions. So can you speak a little bit about how Heat Inverse performs, or how performance is impacted by things like cloud cover, humidity, 24-hour solar cycle, et cetera?
Yeah. So there are absorption features from water in the atmospheric window. So when the totally ideal application is in the very hot and dry environments. That said, we have seen really good. Like I said, we're in Ithaca. It's very humid here frequently in the summer, lots of overcast and all that stuff. So we have seen really big temperature differentials still, despite having being in a more humid environment. And we've also seen that at customer sites as well. Like there'll be large, maybe not quite as much as it would be if it was hot and dry, but definitely a big impact still when it's humid. Yeah.
Perfect. Yeah, and then I think maybe last question, because we're coming up on time here. Can you just speak to how Heat Inverse's film, how soiling impacts the performance of that, if it's self-cleaning, et cetera? And then also if there's been longevity tests for the material, like salt spray testing, cleaning maintenance requirements, that type of thing.
Absolutely, both. Yeah, so we anecdotally we've tested in very dusty environments where we come back to the test setup and haven't noticed any difference in the cooling capacity, but and there's definitely dust on top and that sort of thing. That said, if it's completely covered, and it's not able to access that relationship to the cold sink of outer space, then it won't be doing that, right? So that's a very anecdotal sort of based data there, but and then also, yeah, we've done a lot of longevity testing. That's actually been a lot of where our focus has been in recent years, and we do salt spray testing. We do all kinds of longevity tests where we have different formulations that are outside, have been outside for years. I mean, the best test is just the applications at pilot sites that have been out there for years, and looks good.
Great. Amazing. Okay, so I lied. One very, very quick question for you. Is Heat Inverse fundraising? And then we'll switch over.
So as a startup, we're always fundraising, right? But right now we're not in the middle of a concentrated fundraise.
Okay.
I'll say we will be doing that soon, as we're transitioning from this pilot phase where we're doing smaller deployments to negotiating these multi-million-dollar tens and maybe even hundreds of millions of dollars per contract. And I think, it's sort of a transition period where we're in between two phases. And so we're thinking we'll do that fundraise once we get more solidly into the next phase.
Amazing. Okay, thank you so much, Romy. We'll go ahead and launch the poll for anyone who wants to know further questions. I know we didn't get to all of them, / if you want to be connected to Heat Inverse. And while that's up, I'll invite Blue Frontier and Matt to join and start presenting.
Awesome. Thank you very much, Lindsay. So at Blue Frontier, we are trying to transform air conditioning and dehumidification. Our technology is mostly, at the moment, geared towards commercial buildings, and we seek to improve the efficiency of air conditioning while also simultaneously having the technology capable of energy storage and load shifting and load shedding.
Sorry, Matt, we can't see your slides. Do you mind resharing?
Good thing I was still on the cover slide.
Perfect. Thank you.
How about now?
Yep, perfect. Thank you.
Awesome. So yeah, we're commercializing our technology. It's an hyper efficient air conditioner that has embedded energy storage, and we're trying to transform how commercial and residential buildings do their air conditioning. But we're going to try and also extend that to data centers, and hopefully you'll understand how by the end of this slide deck. So we all remember what happened on January 6th. No, not that January 6th, this recent January 6th. It was the NVIDIA announcement where he got on stage and tried to convince the world that you can cool their chips with 45 degrees Celsius water going in, which means 55 to 60 degrees Celsius water going out. And upon that announcement, air conditioning companies lost about $15 billion in stock value following that announcement. But there was one air conditioning company that was jumping for joy, and that was us. And the reason for that is it actually plays directly into our grand vision for how our technology could help data centers. And that's what I'm going to try to explain today. Very brief background on how the technology works. We split it up into two subsystems. One is which delivers the cool, dry air. That's the conditioning subsystem. And in order to achieve the value prop of energy storage and load shifting, this has to be able to run with almost no electricity. Only fan power, because you're not going to ever get away from needing fan power, but no vapor compression cycle, no compressor, nothing. So when this is running, it can deliver air conditioning at about a 90% less power consumption than a normal air conditioner. And it does that via a constant stream of concentrated liquid desiccant. Eventually, you dilute all the desiccant and you need to regenerate it in the regenerator subsystem. But really quickly on the conditioner subsystem, I'm not going to have the time to get into how it's built, but just on a psych chart thermodynamically, it's two stages. The first is to isothermally dehumidify the air via contact with the liquid desiccant down to a low absolute humidity. And then from there, we cool the air with indirect evaporative cooling, and we do it in the dew point style. It's a way to indirectly evaporate water that drives the air to the dew point instead of the wet bulb, and that can get you lower temperatures. And so on this day, which is a pretty hot and humid day, the air or the water, if you slightly change the architecture, could get down to 55 Fahrenheit. You compare that to direct evaporative cooling if you did not, or indirect evaporative cooling if you did not dehumidify the air, but you still did it the fancy dew point style way, that's about 77 Fahrenheit. And then if you just did straight up swamp cooling, it's only 78 Fahrenheit. So this kind of explains why we can run the conditioner without electricity to do true comfort cooling is because we can get the air temperatures down to the 55 Fahrenheit that the air conditioners expect because we pre-dry the air with desiccant. And that's also a temperature that is much more useful for data centers too. So they don't have to avoid running their evaporative coolers, or they don't have to have a chiller alongside their evaporative coolers for the humid days. But the regenerator is really where our true vision comes in. So when you have dehumidified enough air that you've diluted all your desiccant from the storage tank, you're going to need to regenerate it. You're going to need to remove that moisture from the desiccant. Again, our normal commercialized product does it with electricity and a heat pump inside it. So there is a compressor, but it's only there for heat, and it's only there when you need to recharge the desiccant. It doesn't need to run during the peak hours of the day. But since it's a thermal process, you can also run this on waste heat. And we have a lot of people that are pushing us towards that for reasons like, running this on the waste heat of a generator during a disaster, running it on the waste heat of a heat rejection chiller because they don't know what to do with their waste heat, stuff like that. But GTI, Gas Technology Institute, has done research and published a paper on our regenerator using waste heat. And it had a thermal COP of about 0.8 to 1 between the temperatures of 60 Celsius and 80 Celsius. So this is low-grade waste heat of the type that NVIDIA is saying can come out of their chips, getting you meaningful COPs. And these are thermal COPs, meaning the amount of moisture removed from the desiccant. When you map that on to the actual air conditioning, because the drying of the air enables follow-on indirect evaporative cooling, it's COPs of about 3 and greater, based on the waste heat. So why is that meaningful for a data center? A quick matrix, I don't need to get into it in super detail, but for an air-cooled data center, you don't have the chip waste heat, but you do have a lot of air cooling needs. You can still do this idea where you're regenerating the desiccant on waste heat. That waste heat just has to come from a different source, like a bring your own power plant waste heat. They do have a lot of waste heat, so we can use that waste heat driven regenerator to remove the air cooling loads via waste heat of a power plant. But for hybrid loads where you have chip cooling and air cooling, the chip cooling can now power the air cooling. You can regenerate the desiccant with the warm water that's used for the chip cooling and use that desiccant to eliminate the air cooling load or shift it towards evaporative cooling all year long. But then kind of the one that made all of the air conditioners lose their valuation, and the one that had us dancing is the top right one, which is, okay, if we're shifting towards mostly liquid cooled, it'll never be all liquid cooled, but mostly liquid cooled, and the water's allowed to go in at 45 Celsius, where did the cooling load even go? Do these data centers even need help with air conditioning? And the answer is maybe not. And that's a really good thing for us. And the reason why is this little sketch that our CEO drew about a year ago, because he was already thinking about this. And that's up here in the top left. The data center is just our regenerator. Its heat rejection is our regeneration, and it's just stockpiling concentrated desiccant. And that desiccant isn't used in the data center. It's used out and around the data center. It's just regenerating it and sending it to cooling loads nearby. It can be office buildings nearby. Our desiccant does not lose its cooling potential as it's plumbed around because it's not based on anything thermal. It's just based on the mass fraction of the desiccant. So in this case, is it even a power consumption increase to install a data center? All of its electricity is going into heat. All of the heat is going into air conditioning at a COP of about 3, which is the COP of the air conditioners that were there before. So actually, it's just taking the electricity that was already being used for regional air conditioning. And this is directly speaks. Go ahead.
Sorry, maybe like 1 more minute to wrap. We gotta get a Q&A. Yeah, thank you.
All of the headwinds that Lindsay was talking about, power consumption, construction, permitting, PR, they're the hero now. Everyone around them is getting free air conditioning, and they did not increase the electricity consumption of the region. And that's our vision for how the technology can truly impact the situation with data centers. Okay, that was it.
Amazing. Sorry, I hate interrupting because you were doing great. So we've gotten a couple questions into the Q&A that we're going to get to really quickly. I think personally, I just find liquidescent kilns really exciting because they separate out how you control humidity versus how you cool air. And by doing so, you get like significant energy savings. So first question for you, no refrigeration cycle, but if you have a heat pump, where is the heat cool coming from?
So in our commercialized product, we do have a refrigeration cycle. It's just not used in the air conditioning half of things. It's completely isolated within the desiccant regenerator to create heat to power the thermal process of regeneration. In the past, we've had, heat-driven regenerators without electricity. You're just reducing your market, right? Because a lot of buildings don't have that waste heat available. So the system does have a vapor compression cycle only to create heat, so it actually gets more efficient on hot days. And then that waste heat regenerates the desiccant, which goes into a tank. So you can guarantee that you're not going to have to run that compressor during the peak 5 or 6 hours of the time of use. Tara.
Great, super. And then I know your system includes like energy storage, which is not necessarily like the energy storage people typically think of. It's more thermal energy storage. So in what situations does thermal energy storage provide the greatest operational and economic advantage compared to traditional, say, efficiency upgrades alone?
Yeah, so that's a great question. We struggle with what to call it too. Thermal tends to, I guess, get people on the right track. It's definitely not electrochemical. I like to call it dehumidification potential. You just basically fill the tank with a concentrated desiccant, and that desiccant is going to sit there forever until it dehumidifies the air. So that's what you are storing, is the ability to dehumidify the air. So that is a serious reduction in electricity requirements when buildings want to dehumidify air, which is pretty much all the time. Hugely important for buildings with high internal latent loads, hugely important for buildings with high ventilation requirements, and also hugely important in really hot and dry conditions, because usually like in Phoenix, when it's like 110 Fahrenheit and only 30% relative humidity, that's actually still too high of a dew point. So they need to cool the air all the way down, all of that sensible cooling, just to knock a little bit of moisture out, right? And you don't have to do that at all if you have this in the tank.
Amazing. Thank you, Matt. We are right at time for this. So yes, we launched the poll for Blue Frontier. Again, feel free to let us know if you'd like to be connected or you have questions. I know there were some here we didn't get to, so hopefully we can follow up with those afterwards. And just thank you everybody for joining today. We have 2 more startup showcases coming up on data centers specifically. The first one is power for data centers, and then we'll be doing one focused in on innovations in Southeast Asia. So we really hope to see you for those as well. And with that, I think we'll wrap. And thank you everybody so much.